Okay, so we'll finish up today with section 3.2. We're going to talk about three separate things in this section. Talk about continuity, end behavior, or what's called the intermediate value theorem. Okay, and there's a relationship between them. Okay, so we'll kind of see that as we go. So most graphing calculators, especially older ones, assume that anything you want to draw on it should be connected. So I'm going to show you a graph of something. Let's take 3 divided by x plus 2. Okay. If I graph that, okay, the way that it looks on the screen right there, that's exactly how it should look. That is correct. And notice the speed that I graphed it at. If I go to second format, okay, on a newer calculator, you have this option. And I turn detect asymptotes off. It's going to graph it a lot faster, but it also doesn't graph it properly. Okay? That's how older calculators would graph that. Right? They assume that everything should be connected, and that's a graph that should not be connected. Newer calculators, since they can detect asymptotes, they can handle graphs that shouldn't be connected perfectly. They're a little slower to draw it, but newer calculators can draw it correctly. Right? And I just graph something like this. So I'm not going to graph that one again. But let's just look at the one I have. Could you trace that graph without lifting your finger off of it? No, because it's in 2 separate pieces. That's not a connected graph. Okay. How about that one? That's the step function. Could you trace the step function without lifting your finger off the graph? Anything crazy? No, right? The step function is like a series of horizontal lines. Looks kind of like this. It's broken. Okay, you have to jump from step to step. So, no. How about that one? X squared minus 2x plus 4. Jan, what shape would that be? Be a parabola. Can you trace that without lifting your pencil? Yes. So this one you can't, this one you can't, that one you can. And that characteristic that you can trace your graph without lifting your pencil, or without having any breaks in it, that's called continuity, or a continuous function. So we say that a function is continuous. And you can also be a little bit more specific and say, well, it's not continuous everywhere, but it is continuous between when x equals 2 and x equals 6. I can trace from 2 to 6 without lifting my pencil. Right, so maybe you're just focusing on a specific interval. So a function is continuous on a specific interval if in that interval you can trace your graph between your start point and your end point without ever lifting your pencil. Okay, that's kind of the basic way to think of what it means to be continuous. You can trace between your start point and your end point without ever lifting your pencil. If a graph isn't continuous, then we call it discontinuous. And the idea of continuity, that comes up in calculus a lot. Having a graph that's continuous. Okay, so any question on that idea? If you wanted to describe continuity a little more formally, you could say something like the graph has no breaks in it. It has no undefined values in it. It has no asymptotes. You could use more specific words to describe what it means to be continuous, but the idea is that you can go from point A to point B without lifting your finger to trace it. So I could give you a graph, and maybe the graph isn't continuous everywhere, but maybe you can find a spot that is. Maybe there's a small section between, like, when x is 1 and x is 5. You could trace between 1 and 5 without lifting your pencil. So we're going to take the graph of 1 over x, and we're going to write 2 intervals where the graph is continuous, and then 2 intervals where it's discontinuous. Let's graph 1 over x. Okay, there's our graph. And remember, this graph really, it goes up forever and down forever. It's just that it's getting so steep the calculator can't draw it. If you want to prove to yourself that it goes higher than like 6 or 7, just plug in a value very close to 0, but not 0. Okay, when x is very close to 0, y is up at 100. Okay, so it does keep going up, even though it looks like it stops. All right, so let's start with continuous. Can somebody give me an interval over which that graph is continuous? How about Adney?
1 to infinity.
Okay, you could trace from 1 to infinity, and how would you write that as an interval?
In parentheses.
You could, yeah.
1, comma, infinity. Parentheses.
Parentheses, yeah. So that's an unbounded interval over which it's continuous. Can somebody give me a bounded interval over which it's continuous? What about Sam?
2 to 5.
Sure, from 2 to 5. Open interval or closed intervals?
Close.
Closed, okay. So you could trace from 2 to 5, including 2 and 5, and you'd never have to lift up your pencil. So there's an infinite amount of answers, okay, where it's continuous.
How did you get 2 and 5?
How did you get 2 and 5?
Well, if you look at the graph, the line above the second x
Yep, so there's 2.
is connected to the 5th.
And there's the 5th one over here. And why is that continuous?
Because the line is connected on both points.
Right, because you can trace between the 2 points, and there's no breaks, there's no undefined values, there's no steps. You never have to lift your pencil to trace between those 2 points. Again, that's one of an infinite number of answers.
So you can do like 1 and 8?
Mm-hmm.
Oh, okay.
Yep. Now let's do discontinuous. Can somebody give me an interval that would be discontinuous? Leo?
-1 to +1?
Yep. Open, closed, half open. It really doesn't matter, but what do you want to do?
Closed.
Closed. -1 to +1, including -1 and +1. Okay, that is a discontinuous interval. Can somebody else give me one more discontinuous interval? Yeah? -2 to 2, sure. You do -2 to 2. What's the key? If you want to give me a discontinuous interval for this problem, what do you have to make sure happens? Yep.
Yeah, negative and a positive.
Right, you have to go through 0. Because your graph is undefined at 0. So as long as you try to go through 0, like going from a negative to a positive, it's going to be discontinuous in this particular one. Okay. so let's graph the integer function, and I want to find the length of the longest continuous interval that I can. So I'm going to go math, number, int, x. Okay, get graph. And what would be the longest continuous interval that you could possibly come up with on that graph? Leo?
It would just be one.
1 unit. 1 unit is the longest interval that is continuous on this graph. So can somebody name a continuous interval on that graph? And yep.
0 to 1.
Can you tell me how to write it?
Bracket 0.
Yep.
1. Bracket.
We got to be careful. So remember how the integer function works. Okay, it rounds to the greatest integer that's less than or equal to your number. So, like for example, if you had 2, what's the greatest integer that's less than or equal to 2? What time? Integer. Greatest integer that's less than or equal to 2. Nope, 1. It's the greatest integer that's less than or equal to 2. 2. Yeah, it's equal. So when you're at 2, you're not here. You are here. Right? So when you get to 2, that's when it jumps up. So let's go back to this. So 0, I agree with the bracket. But when you get to 1, would you include it or not include it? You would not include it. So I guess technically the longest interval that you can have is 0.9 repeating, but basically 1 unit. Okay. I'm not going to get picky about that right now. Okay. Any questions on that one? What would be again, you didn't have to write that. I'm just giving you an example of a continuous interval. What would be an interval that's discontinuous? From what to what? About Trevor.
Would it just be stating like 2 of the little lines?
Just 2 numbers. You gotta just give me 2 numbers.
2, 1 to 3.
1 to 3, sure. That's discontinuous. Because to trace from x equals 1 to x equals 3, I'm definitely going to have to lift my pencil. Yeah. Yeah.
Could you do like 1 to 1? Does that make sense?
1 to 1?
Yeah, because it doesn't it goes right on top of each other or not?
1 to 1. Like what are you thinking? Open, closed? Like how would you write that?
I don't know, close maybe?
Because if you picked something like that, that interval is basically a single point. Because it's everything from the number 1, including the number 1, to the number 1, including the number 1. So that would just be a single point. So technically that would be a continuous interval that's infinitely small. Yeah. As far as could you do 1 to 1 for a discontinuous interval? I don't really think so. No, I don't think so. So there's 3 ways, and I kind of mentioned these earlier, that a function can be discontinuous. The first way is the example I showed you. You can have an undefined value. Okay, one way to get an undefined value is to have it divide by 0. Another way to get a discontinuity in a graph is the example you see in the integer function. Now, in the integer function, it's not that you plug a number in and you get undefined. The domain for the integer function is all real numbers. It's just the way that the integer function rounds your number off that causes a break. But it's not due to an undefined value. Okay, so you can have an undefined value, you can have a break, or you can have a hole in your graph. And a hole in the graph is the trickiest one to see, because if you just look at a picture, it's not even going to look like it's there. When we say a hole in the graph, we mean a hole that's infinitely small. So let me graph this and show you what it looks like. We have x squared plus 3x plus 2 divided by x plus 2. What does that look like? Looks like a line. It's not a line. It's not a line because what value are you not allowed to plug in here? Yeah? You can't plug in -2. If you go to your table and you try it, you get an error. But you can plug in something very close to -2. And you could also plug in something very close to -2 on the other side. So it's defined on both sides, okay? And it's not going to infinity or negative infinity like an undefined value with a fraction would. Okay, like when we have a divide by 0. The difference here is, look at the top. How does the top factor? X squared plus 3x plus 2. Jane?
X plus 2 and x plus 1.
Yeah, x plus 2, x plus 1. So basically what happens is the x plus 2 cancels out, and if you graph y equals x plus 1, that's basically exactly what your graph is going to look like, except that there's a small hole in the original. And you can't forget that. So the way you know that your graph has a hole in it is if your numerator and denominator have a common factor. X plus 2, x plus 2. Now, if you just change one number, okay, change that 2 to a 3. Now, the top doesn't factor. So the top and the bottom is not going to have this kind of idea where things cancel, and the graph is going to look totally different. Okay, now you have there what's called a slant asymptote, okay, which we'll talk more about later on. But for now, I just wanted you to understand what a hole is and how it occurs. It occurs when the top and the bottom have a common factor. So any questions on what I mean by a hole, a break, or an undefined value without common factors? These are 3 basic discontinuities. Okay, so I mentioned this idea when we talk about domain. Every polynomial function is continuous from negative infinity to infinity. So in other words, you can't, if I give you a polynomial function, you can't find an interval where it's discontinuous. It's impossible. Polynomial functions are always continuous forever. So if you're graphing a function that is discontinuous, I guarantee you it's not a polynomial. And if a function is always continuous, not just continuous over a small interval, but it's continuous on any interval that you could possibly name, then we call it a continuous function. Okay, so any questions on the difference between saying that something is continuous on an interval versus saying you have a continuous function? Okay. Okay, so this test, since there's a lot of concepts that we're studying that kind of the way you know them is if you write about it or explain it, there will be some questions on the test where you have to kind of write something out. It's going to be a lot of like calculation stuff too, but you're also going to have to like explain a concept to me. So I might ask you, what is the difference between being continuous over an interval versus if you have a continuous function? What would be the difference? Yeah.
So polynomials are always continuous functions?
Yep, polynomials are always continuous functions. All right, so we're going to connect the first idea that we just learned to the second idea, which is called the intermediate value property. What is the idea? What does intermediate mean? Yeah? In the middle, right? It means you're not like a beginner, maybe you're not advanced, you're intermediate, you're in the middle. Or like an intermediate, someone that is in the middle of two things. All right, so this property is going to have something to do with being in the middle. Or being between. Okay, so it says that if you have a function that is continuous on a closed interval between 2 points. Okay, I call them A and B. Then what that means is your function can take on every y value between f of A and f of B. Okay, so as an example with numbers, let's say f of A equaled 2. F of B equaled 13. Then on the interval, right here, over that interval, I don't know what A and B are. I know what f of A and f of B are, okay, but I don't know exactly what A and B are. But whatever they are, over that interval, I'm going to go from a y value of 2 to a y value of 13. Now, if you're going to go from the number 2 to the number 13, and you can never lift your pencil, do you have to go through every value in between? Sam?
Yeah.
Yeah. It's impossible, no matter how you draw it. If you start at 2, somewhere on the x-axis, we don't know where, and then you're going to end up at 13, somewhere else on the x-axis, and you have to trace from that point to the other point without lifting your pencil. You gotta go through every y value at some point. Even if you try to start going down and then back up and down and up. No matter how you do it, you're going to go through every single y value. You might even go through more y values. Okay? In this case, you even go down as low as 1 and as low as 0. I can't guarantee what other values you're going to go through, but I can guarantee if you trace from 2 to 13 and you never lift your pencil, at a minimum, you have to go through the numbers, every number between 2 and 13. It's kind of like if you had a pot of water at 40 degrees and you're going to get it up to boiling. Well, as you go from 40 degrees up to 212 degrees, do you go through every temperature in between? Or do you skip temperatures? What do you think, Jay?
You can go through everyone.
Yeah, you have to. If you go from 40 to boiling, you go through every single temperature in between. Maybe you don't have a thermometer that's accurate enough to measure that, but you still have to go through it. You can't all of a sudden go from 40 degrees to 90 without going through every other temperature. Right? That's the idea of continuous. Okay. So if that idea makes sense, wording it that way, that's fine.
Can I please have everyone's attention?
If you want another way to word it, you could word it this way. What this is saying is that if you have a closed interval between A and B, then there is you could pick any number you want, L, between f of A and f of B. So going back to my example, pick a number between 2 and 13, 7. So there's some number that you could pick for x that would give you 7 for y, somewhere. You could pick any number you want between 2 and 13. That's your y value. And I guarantee you there's an x value that would give you whatever number you pick. It has to. Okay. So like let's say you picked 7. Okay. So it looks like I crossed 7 right there. So maybe that's an x value of 6. So you pick any number you want between f of A and f of B, between 2 and 13. And I guarantee there's an x value you could plug in to give you the number that you picked. Right. So let's look at this formula. F of x equals 3x minus 4. And what I want to do is determine a number, c, okay, on the interval from negative 10 to 10, such that when you plug in c, you get 15. So I want you to find an x value between negative 10 and 10, so that when you plug it in, you get 15 for y. Right. So first thing I'm going to do is just make sure that that's even possible. Am I really even going to go through 15 at some point? So let's check plugging in negative 10. Let's see what the y value is. Let's plug in positive 10, see what the y value is, and make sure that 15 is a number we're going to actually go through. I know I'm going to go through 15 somewhere, because what kind of graph is that, 3x minus 4?
Linear.
It's linear. So there's no question it goes up forever and it goes down forever. But the question is, does it go through 15 on that interval? Okay, so let's check. So Dylan, if I plug in negative 10 for x, what do I get for y?
You would get negative 34.
Yep, negative 34. And Sean, if I plug in positive 10, what do I get for y? 26. So knowing that this is a linear function, and I'm starting at a y value of negative 34, and I'm ending at a y value of 26, am I going to go through a y value of 15? Okay.
Yes.
Yeah, I have to. Right? I'm going from negative 34 to 26. I'm going to go through every number in between, including 15. Now I just want you to tell me where you go through 15. So where would I plug in 15 to find that value? Well, Rebecca?
Well, wouldn't it have to equal 15?
It would have to equal 15. So we're finding the x value. We're finding a number that you plug into the function. So 15 equals 3x minus 4. So x is 19/3. Now, we just want to make sure, we already kind of checked this, but is 19/3 between negative 10 and 10? You think, Tessa? Is 19/3 between negative 10 and 10? Yeah, that's going to be, if you were to divide it out, that's like 6 point something, 6 1/3. So yeah, it's between negative 10 and 10. Okay, let's try this one. So this time I want to determine a number over the interval from -2 to 3, such that when I pick a number over that interval, I can plug it in and get -3 for y. All right, so first thing, Sam, what shape is this graph?
Quadratic.
Yep, it's a quadratic, which is a
A continuous function.
continuous, but the shape would be a
Parabola.
parabola. Yep. Okay, so let's see what happens here. F of -2. Tanya, if I plug in -2 and square it, I get, and then 3 times -2. And then if we simplify, 4 minus 6 is -2. Minus 4 gives me -6. So we've got a y value of -6. And Shauna, if I plug in 3, what's 3 squared? 9. And then I have 3 times 3, which is another 9, so that's 18. And then 18 minus 4. 14. Okay. So, am I going to go through -3 at some point? Yes. Is it possible that I go lower than -6 or higher than 14? These are 2 points on a parabola. These are not on a line. So think about maybe you're at -6 here, but that's not the bottom of your parabola. Maybe it goes even lower. And then over here, you're up at 14. So it's possible that you go even lower than -6. We don't know. We don't know if that's the bottom of the parabola or what. But we do know we're going from -6 to 14. You're going to go through every value at least between those two. So to solve that, Trevor, how would I find, or where would I plug this in?
Make x squared plus 3x minus 4 equal to it.
Perfect. So we're going to set that equal. What I'll do is just use the calculator. Since it's a quadratic, I could use quadratic formula if I wanted, but I just don't want to go through that right now. All right, so we've got x squared plus 3x minus 4. And I'm going to set that equal to, what was it, -3. And you should set your window to what they told you to look between. They said to look between -2 and +3. Because remember, it's a parabola, so there's going to be another answer somewhere. But I don't care about the second answer. Okay? I only want the answer between -2 and 3. So second calc, intersect. And it looks like x is about 0.303. We round it. Actually, I call it C in this case. That's the number you could plug into your function, and you will get -3 for y. Any questions on that one? Okay, this one. Now, this one, I don't want you to find the 0. I don't want to know what number do you plug in for x to get 0 for y. I just want you to prove there is a number. And I want you to prove that there is a number that you could plug in for x and get 0 for y. And I want you to show me that that number is between 0.25 and 0.75. Okay, so how could you do that? How could you prove to me that there has to be a 0 between these two numbers? But you don't have to tell me what it is. Yep.
You could graph that function and have your min and maximum be those numbers and see if it crosses the x-axis at all.
Okay, if we did it graphically, how could we do it using the idea of what we're doing? like what we did in the last two problems. We're not going to use a graph for this one, but that is a good idea if you were going to graph it. Mm-hmm.
You can plug in the 0.25 and 0.75 for
Okay,
X.
let's do that first, and then I'll come right back to you. So let's plug those in. I am going to use a graphing calculator, but not for the point of graphing. It just speeds up doing what Megan just said. So x to the 5th plus 2x minus 1. All right, so if I plug in 0.25, I get negative 4.99. Negative 0.499. And if I plug in 0.75, I get 0.737. Okay? And what else were you going to say, Megan, now?
Because one's negative and one's positive, it has to go through the x-axis.
Why do I have to go through the x-axis?
Because that's just
But if I was counting by like, let's say I was counting by like 3s, I could go like -5, -2, 1, 4, 7. So I was counting by 3s and I skipped 0.
because it has to go through everything in between. So it has to touch 0 at some point.
I agree with you, it has to touch 0. I'm just looking for one important word.
All polynomials are continuous.
Yes, all polynomials are continuous. So that's the key. You just have to mention that it's continuous. And let me write it down. So since f of 0.25 is negative and f of 0.75 is positive, and you have a continuous function, that's important to mention, and you have a continuous function, you have to pass through 0 at some point. There's no way to go from negative to positive if you're continuous without going through 0. And you have a continuous function, you must pass through 0. Or I think the way Megan worded it, you have to cross the x-axis, which is saying the same thing. Okay, so that idea, that concept and being able to articulate that is very important. So any question on what we just did? Yeah?
The table on my calculator won't let me put in anything for X. It just has a list of them that are already there.
So go to second, table setup, and put your independent on ask, and keep your dependent on auto.
Oh, okay.
And that'll work. Okay. Any other questions on that? Okay. So that's the first two things. So that's continuity and end behavior. And that last example showed how you could tie the two together to prove something. And the last thing we've already kind of talked about is what do polynomials look like? Okay, what's kind of the pattern? And can we figure out something maybe based on even and odd degree polynomials and things like that? So end behavior of a polynomial is what's happening at the extreme ends of it. Okay? So if you had a graph, maybe did something like this. We don't really care about this section. That's not what you're looking at when you're looking at end behavior. You're looking at what's happening all the way on the left. Okay, it's going down. And what's happening on the right? It's going down. So this would be a polynomial we would describe with the end behavior going down on both sides. Okay. And I'm going to show you two ways how you can describe that. All right, so y equals x cubed, I'm just going to sketch it for you kind of quickly. It looks like that. So the way you would describe the end behavior is on the left side of the function, it's heading down. On the right side of the function, it's heading up. So this kind of question would say, describe the end behavior on the left and then on the right side. I don't like on the test, sometimes the test generator is a little tricky, the way they word it. They say, describe the end behavior on the right side and then the left side. So if they said that, if you want to describe the right side first, the right side is up. The left side is down. Okay, I don't like describing it that way because then it's kind of backwards. Okay, I like describing the left side first and then the right side. Okay. In that order. Okay, always in that order. Now, another way you can describe it is using what's called limit notation. Okay, you'll use that a lot next year. And the way you read this is f of x is just a symbol for what letter? Y. So this says the limit of y, or basically what is happening to y as x approaches infinity. That's how you read that. The limit of f of x as x approaches infinity. Okay, or simplifying it, what's happening to y as x gets bigger and bigger. So look at the graph of y equals x cubed. As x gets bigger and bigger and bigger, as x heads to the right, what's happening to your y value? Yeah. It's going up, and how high does it go? Caleb? Infinity. So what's happening to y as x gets bigger and bigger and bigger towards infinity? Y is heading up. Now, what's happening to y as x gets smaller and smaller and smaller towards negative infinity? What's happening to your y value? What's the limit? It never reaches it, but it's getting closer to it. Negative infinity. So in this case, as x gets more and more negative, negative 100, negative 1,000, negative 1,000,000, y is getting lower and lower and lower, and it's never stopping. All polynomial functions either head towards infinity or negative infinity for the end behavior. All polynomial functions. Okay. Some go up, some go down, some both go up. There's 4 different types of end behavior. Okay. So a parabola would be an example of an end behavior that's up, up. You could flip the parabola over. That's an example of end behavior that's down, down. And then if you want one up, one down, that's like a cubic. I just showed you one. And you could mirror image it, and instead of down, up, it could be up, down. And so those are your four types of end behavior. So let's graph y equals x to the 4th and describe the end behavior. So y equals x to the 4th. That window is fine, whatever I'm using, because we can see what's happening. What's the end behavior? And let's first do it as one of these 4 types. What type of end behavior do we have on this one? Yeah? Yeah, it's up, up. So we could say the behavior on the left is up. Behavior on the right is also up. I hate when they reverse that order because then it's like almost like a trick question. Another way we could say it, what's happening to y as x approaches infinity? So look at that graph. What happens to y as x gets bigger and bigger? Yep.
It approaches infinity.
It approaches infinity. And what happens to y as x approaches negative infinity?
It approaches negative infinity. Like it's, oh no, it
Oh.
also approaches infinity.
It also approaches infinity. Okay, as you head further and further to the left, this graph is still going up. Okay, it's up on each end. So these two things are exactly the same.
Which one do you prefer us to write, or do you not care?
I will always put in the directions to either write it using this is called limit notation, or you could write it, I don't even know if there's a name for that notation. It's like arrow notation. Now, if we put a negative in front of that, what's the negative going to do? Flip it over which axis? Yep, it's going to flip it over the x-axis. So now we get a behavior that's down, down. Okay, so this one, so y equals negative x to the fourth, down, down. This was y equals x to the fourth. And the only thing that would change in the limit is both the infinities would be negative infinities. But this one and this one would become negatives. So we can kind of generalize it based on whether a polynomial is even or odd, and is the leading coefficient a positive or a negative. That tells you the end behavior. Anything else in the problem may cause little twists and turns, but if you want to know the end behavior of that thing I just wrote, all you have to do is look at this and look at that. Those are the only two things you need. Okay, so here's the chart. So first, you have a column dealing with even polynomials and then a column for odd. And then you have a row that says your coefficient is greater than 0 or less than 0. So the particular problem I wrote, negative 3x squared, that's a negative coefficient, even degree. The problem I wrote, you're right there. I don't know all the little twists and turns that are going to happen in the middle, but I do know it's going to go down on the left, down on the right. Okay, so any questions on what you need to focus on to determine end behavior? Yep.
Should we memorize those patterns? Or
I think after you do enough problems, you'll remember that even degree, like I just think even is x squared, it's a parabola, so evens always go in the same direction. If there's no if it's a positive coefficient in front, think of your basic parabola, up, up. When you put a negative, it goes down, down. Maybe the odd one might take a little bit more time to practice, but yeah, eventually you should know which way is which. Yep. Okay, so I already said this. The leading term controls what's going to happen. It dominates the polynomial. So all you need to do is look at the leading term if you want to know end behavior. That's it. Just look at the leading term. So that leading term is what we call, it's a model. It models the behavior. Right, so basically, if you had something like 2x cubed minus 3x squared plus x plus 1, like this. Doesn't really matter what it is exactly. What's the only term there that is going to predict the end behavior? term? Caleb?
2, and the coefficient for 2x cubed.
The whole term, the 2x cubed, yep. So that predicts the end behavior. You've got to look at the whole term. So basically, if you graph that and you graph that, they're going to look the same if you zoom out far enough. Okay, all that other stuff, if you zoom in, you'll see differences in the graphs. Okay, so there's the original. And here's the simplified one with just the leading term. Now, it doesn't really look exactly the same, but the more you zoom out, the more and more the red and the blue start to look the same. There's the blue. There's the red. Now they almost look like they're right on top of each other. Okay? So the point is, all you need is the leading term. So if you want to write what's called an end behavior model, I just did it in this last problem. The end behavior model for the graph in blue is the one in red. All you have to do is take the leading term, write that down. That's the end behavior model. Again, all the other stuff, it's going to cause little twists and turns, but if you zoom out, big picture-wise, none of that other stuff matters. All right, so I'm not going to go through the next problem. It says to graph, and actually I already did it. I just graphed a slightly different one. It says to graph f of x and graph g of x. And if you zoom in, like I had originally, you're going to see that they look very different. But then if you take your window and back it off and zoom it way out, they pretty much look the same. Okay? So I just did example 7 with you. So let's just do example 8. What would be the end behavior model for example 8? Yeah?
I have a question about the equation.
Mm-hmm.
The one, it's like a sub 1 x plus a sub 0 at the end.
Yep.
What does that mean?
So these are your terms in the polynomial, your a sub whatevers. Those are your coefficients.
Mm.
And then the exponent is decreasing by 1 each time till you finally get to the last term. There isn't even a variable. It's just a constant.
Oh, okay.
Kind of like this one. So what would be the end behavior model of example 8? Yep. Yep. And based on the fact that that's a negative coefficient and an even exponent, what would be the end behavior? Yep.
Down, down.
Down, down. Down, down. I'm going to hold off on that one. Okay, so any questions on example 8? All right, so homework tonight, so we just did one section, so it's all on page 161. Okay, it's 1 through 6, 9 through 12, 15, 16, 21 to 25, 29 through 31, and 33. Don't forget, I will be after school for extra help if anybody needs to stop by. We'll go over that first thing, and then tomorrow we'll have our test. And don't forget, progress reports close tomorrow.